Welcome to my channel. My name is Dr. Andrew. Today we're going over one of the most foundational topics in all of math, real numbers. So here's everything you need to know about real numbers. Well, technically this video should be infinitely long, so here's almost everything you need to know about real numbers. So real numbers consist of all the numbers that can be represented on the number line. So real numbers consist of all the numbers that can be represented on the number line. Alright, so let's draw a number line and talk about some real numbers here. Okay, so here's our number line. Let's start by drawing the number 0 right here at the center of the number line, and this is going to extend all the way to what? Positive infinity on the right hand side and negative infinity on the left hand side, right? So all the numbers exist on this number line, and note the caveat that the only numbers that don't exist here are complex numbers. So we're not talking about complex numbers. Okay, so we have the number 0. Right next to the number 0 is going to be the number 1. And then we're going to start counting up 1, 2, 3, 4. Okay, and so I said we're counting. So these are going to be our first set of numbers, and that's going to be the natural numbers. Okay, the natural numbers are also known as the counting numbers. So these are the numbers that we first learn about in school. So we can start to divide these up. Let's talk about the classifications of numbers. Okay, let's talk about what numbers exist here, and we're going to start with natural numbers. The natural numbers are denoted by this funny n symbol here. Natural numbers denoted by this funny n symbol here. And so these are the counting numbers starting from 1. Okay, so again, we started by counting the number 1 and then 2, 3, 4. So each of these numbers is a different counting number, and these are the natural numbers, and this is going to be denoted by the set as follows. Okay, so we're going to start from 1, 2, and then just count up to infinity. Okay, and that's going to go all the way up to infinity. So this curly bracket indicates that this is a set, okay, which we'll talk about in the future. Okay, and so these are the natural numbers. What other number did we forget about so far? We forgot about the number 0. So we have another set that includes the number 0, and that's going to be the set of whole numbers. So the set of whole numbers is going to be denoted by this funny looking W symbol here. Okay? And this is the natural numbers including 0. The natural numbers plus the number 0. Okay, so this is going to be denoted by the set 0, comma 1, 2, 3, and then count all the way up to infinity. Okay, so now we have the natural numbers, which include 1, 2, all the way into infinity, and the whole numbers. I like to think of whole as like a donut hole, right? And the number 0 kind of looks like a donut hole, so that's why that's called a whole number. All right, what else? What other numbers are we missing here? So we're forgetting about the left-hand side of the number line here, right? So we're going to count from -1, -2, -3, -4, and go all the way up to infinity. So these are going to be called integers. Okay, integers are denoted by this funny Z looking symbol here. Okay, and so integers are whole numbers. And they're negatives. Okay, so for instance, we have all the way from -infinity, okay, and then we have -3, -2, -1, 0, 1, 2, and 3, all the way up to positive infinity. Okay, so for instance, the number -3 is going to be that integer because it's a negative. The number 0 is a whole number, but notice that the number 0 is also an integer because it is indeed included in the set of integers. And the number 1, 2, 3, and 4, well, these are indeed natural numbers because they're counting numbers. They're also whole numbers because they're included with the set of natural numbers plus 0, and they're also integers because they're included of all the whole numbers and their negatives. Okay, so we're going kind of down the list here. So what about the numbers in between these numbers, right? So we don't just have 0 and 1, we might have the numbers, right, 0.5. So what is 0.5 written as? Well, 0.5 can be written as a ratio of 1 over 2, right? So I said the word ratio. Okay, that's going to denote fraction. So we're going to have rational numbers next. Rational numbers denoted by this squiggly looking Q sort of symbol. Why is it Q? I don't know. And so rational numbers are numbers that can be expressed as fractions. Numbers that can be expressed as fractions, or rather ratios, because we have the word ratio, okay, or ratios. So for rational numbers, they come from ratios of the ratio of P over Q, where P and Q are integers, and Q is not equal to 0 because we can't have anything divided by 0. Okay, so this is going to be the set as follows. So this could include, for instance, the number, -3/4. Okay, we can include the number 0.45, because 0.45 can be written as a ratio of 45 divided by 100 here, right? And what other numbers can we have here? We can also have the number even +3, because the number 3 is indeed a ratio that can be expressed as 3 divided by 1. So again, all rational numbers, all integers are also rational numbers, because all integers can be expressed as ratios divided by 1. And as we'll see, according to one of these properties, that's where that comes from. Okay, so if we go back to the number line here, we might have the number 3.5 here. That might be the number 3.5. We might have -1.5. So these are all going to be rational numbers. So what are we missing here? So what if we have the number pi, which lives right around there? This is the number pi, and that's approximately equal to the number 3.14, 3.14159. And so the number pi lives right around there. So pi can't be expressed as a ratio, so that's going to be an irrational number. So it's an irrational number. Okay, and so irrational numbers are numbers that cannot be expressed as a fraction. Numbers that cannot be expressed as a fraction. With non-terminating, okay, this is the important part, with non-terminating, non-repeating digits. Decimals. Okay, so again, we had the number pi. Okay, so the number pi is an irrational number because it's equivalent to 3.141592653, and so that's going to go on forever and ever and ever. And pi is a really, really special number that has some really insanely beautiful properties, super useful in science and engineering. Okay, the number square root 2 is also an irrational number. Okay, and that's going to be equal to approximately 1.414213, and again, this also goes all the way up to infinity. Okay, and last but not least, we have the number e, and e is known as Euler's number. This is equal to 2.71828, and these numbers go all the way up to infinity as well. Okay, so these are all the classifications of real numbers. Okay, so real numbers satisfy important algebraic properties. And so you can think of properties as rules, which are going to sort of act as tools that can allow us to manipulate numbers in really useful ways. So real numbers satisfy important algebraic properties. Okay, and so properties are going to be basically tools that we can use to manipulate other forms of math. Okay, so the first property we have is going to be the closure property. Okay, and the closure property says that for any two numbers a and b, okay, then we're going to have a plus b and a times b are also real numbers. Okay, so that's going to be the closure property. Just move that over here. So for instance, if we have the number 3 plus 4, which 3 plus 4 are real numbers, then that's equal to the number 7. So 7 is a real number because 3 plus 4 are real numbers. And a times b, and let's say 2 times 5, which are also real numbers, and the number 10 is a real number. Okay, so according to the closure property, these are all real numbers. Okay, the next we're going to have the commutative property. Okay, and so the commutative property for addition says that for any numbers a plus b, numbers a plus b is also equal to the numbers b plus a. So for instance, the number 3 plus 4 is equal to the number 4 plus 3. Okay, so 3 plus 4 is 7, and 4 plus 3 is also 7. So that's the commutative property of addition. And then the commutative property of multiplication is as follows. So multiplication says that if we have the number a times b, then it's also equal to b times a. So again, for instance, the number 3 times 7, which is 21, that's also equal to the number 7 times 3, which is also 21. Next, we'll have the associative property. Okay, and so for addition, it says the following. Okay, if we have the numbers a plus b in parentheses here, plus the number c, well, we can just simply move around that parentheses to have the equivalent statement a plus b plus c in parentheses. So for instance, the number 3 plus 5 in parentheses plus the number 4 is equal to the number 3 plus 5 plus 4 in parentheses here. So in this case, we have 3 plus 5, which is 8, plus 4, which would yield 12 on the left-hand side. On the right-hand side, we'll have 3 plus, well, this in parentheses is going to be 4 plus 5, which is 9. And so in this case, we're going to have 12 on the right-hand side as well. Okay, so according to the associative property for addition, this will hold. Okay, and then so the associative property for multiplication says the following. Okay, and it's going to say that a times b in parentheses times c is equal to a times b times c in parentheses here. So in this case, the parentheses here will still be equal to parentheses there. So for instance, if we have the numbers, let's say 2 times 3 times 5, that should be equal to 2 times 3 times 5. And indeed, we see that as the case. 2 times 3 will yield 6 times 5, which will yield 30 on the left-hand side. And on the right-hand side, we have 2 times 3 times 5 is 15. And 2 times 5 is 30. And then so we'll have 30 on the left-hand side and the right-hand side. All right, so that's the associative property for addition and multiplication. Next, let's try the distributive property. So the distributive property tells us how to distribute numbers. So for instance, so it says a times b plus c in parentheses is equal to, okay, so the way this works is we're going to take our number outside the parentheses and distribute it and multiply it into the values in the parentheses there. Super useful facts. So in this case, we'll have a times b here. So that's a times b here. And that's going to be the number a times the number c plus the number a times the number c here. Okay, super useful facts. So if you've seen how to distribute values in algebra, this is where it comes from. It comes from the distributive property. So let's do one quick example here. If we have the number 3 3 times 5 plus 8. Okay, so one way of doing that is through the distributive property here. So that's going to be 3 times 5 plus 3 times 8. So let's write that out here. So that's 3 times 5, which is going to be 15 plus 3 times 8 here. Okay, and so if we keep multiplying these out, on the left hand side we'll have that it's equivalent to 3 times 5 plus 8, which is 13. And on the right hand side, that's going to be 15 plus 24. And so 13 times 3 is going to be 39. And on the right hand side, that is also 39. So according to the distributive property, these are equivalent statements. All right, next we have the identity property. We're going to start with the additive identity. Okay, and the additive identity says that any number a plus 0 is still going to be the number a. Okay, so for instance, the number 5 plus 0 is still the number 5. So any number plus 0 is still that number. Okay, and the multiplicative identity says that a times any number times 1 is still going to be any number. So again, for instance, any number such as 6 times 1 is still going to be 6. Okay, very subtle, but still super useful in mathematics. Next, we're going to have the inverse property, and then we have the additive inverse, okay, which says that, okay, a plus any number a plus its opposite minus a is equal to 0. Okay, so for instance, 5 plus its opposite minus 5, those are going to essentially cancel out and yield the number just 0. And then finally, we're going to have the multiplicative inverse, okay, which says that a times its reciprocal 1 over a is equal to 1, provided that a is not 0, because we can't divide by 0. So for instance, 7 times 1 over 7, its reciprocal, is equal to 1. This is a super duper useful property in science and engineering. So if you're not sure how to move forward sometimes, one of the ways you can move forward is using the multiplicative inverse, and that's going to allow you to do some really cool math. All right, and if you want the written version of these notes, check out the Obsidian link in bio, so you can have access to all these notes here, as you can see. And if you have any ideas or suggestions for future videos, leave them down in the comments below. All right, so that's it for this video. If you found this useful, definitely like and share this video and subscribe for more content.